Thank you. So yeah, I've been involved in transparency for well over 24 hours now. So I feel very confident speaking in front of you now. So what I've actually been doing this past like 5+ years is building a cryptocurrency custody solution for banks. And we use these things called HSMs. Now, HSMs are where you put your private keys if you're a bank. In reality, they're essentially Linux computers from the 80s with a cryptographic coprocessor, and if you try to open them, they blow up. That's all they are. The traditional way of interacting with a key that is stored in an HSM is you have some credentials on a software server. The HSM has your private key. You request a signature, you get a signature. Now, this has a few issues. It looks super simple, but it does have a few issues. And that's, well, the credentials are in a software server. If you break into that, you now have a signing oracle. Never great. So we've been trying to turn these kind of brainless, stateless machines into something a bit more powerful. And the very first step to do that is trying to add some state. Now, by state, I refer to essentially a set of rules that a request must satisfy before being successfully processed. So that way, even if you gain access to the HSM and you can send requests to it, you can't exactly fake those rules being met. A classic example that we've used in the past was we load 3 public keys into our HSM. Any request that makes it to the HSM must be signed by the corresponding 3 private keys. And if they aren't, then the HSM just doesn't process the request. That's great, works well, but it's super, super inflexible. What if you want to modify that state? Then you need to modify directly in the HSM. If you make that step too easy, well, it's not much of a security benefit. If you make that step too hard, no one's going to ever use it. So we fixed that by introducing a kind of meta state, which is we keep 3 private keys, 3 public keys in the HSM, and instead of signing the request, they are in charge of signing state, which is, again, the rules, the workflows, whatever. So we introduced the role of administrators, who are in charge of essentially validating state. They sign a set of users, they sign bindings between users and groups, they sign transaction rules, and we bundle all of that into every single request. We send it to the HSM. The HSM verifies that the request matches the state that it's been sent. It verifies that the state is actually signed by the admins. If everything checks out, then it signs the transaction. Again, great. That's worked for over 4 years before we've hit any kind of limitation. But there are limitations. And the main one is that, again, we have 3 admins. These guys are in charge of validating users. They're in charge of validating binding from users to groups, in charge of validating transactions workflows. We've added a lot of stuff that they're actually in charge of validating. It becomes a bit too much. In practice, we've seen that they almost never verify anything. They just press OK. They just sign. This doesn't work. So we're trying to make it a bit easier for them. And how do we make it easier? We split them up. Instead of having 3 admins that are in charge of validating everything, we want to split them into, OK, so you guys are managers for users. You only verify users. You guys are managers for groups. You only verify that the users in your groups are actually correct, etc. And we also don't want them to be all or nothing. We don't want them to validate the entire state every time there's a single modification. We want them to verify that modification, and modification is applied to the state. And to do that, it's pretty simple. You add rules about modifying the state into the state, you send the request that modifies the state to the HSM. The HSM verifies that the request is valid, modifies the state accordingly, sends it back. Great. But there's still a few limitations. We've never actually implemented this in practice because it doesn't work for a very simple reason. We are sending the entire state on every request. That's too much. There's way too much information for that to be sent in every request. We can't store it inside the HSM. The HSM doesn't have enough memory. It doesn't have enough persistent storage at all, so let alone memory. So we want to trim that down. So we want to, for every request, instead of sending the entire state, we want to send only the relevant parts of the state. So for instance, imagine a transaction that only 3 users need to approve. You don't really need to send the 10,000 users. You just send the 3 users. You say, oh, OK, so those guys are in the state. And you send them. The HSM verifies that they're in the state. And you're done. And that's kind of this model. We only send the relevant state. Now, we're trying to solve 2 problems that are kind of contradictory in nature. Our first fix was like, OK, so the HSM signs the new state. So clearly, it needs to have access to the state. And our second fix was like, hey, we never actually give the HSM the full state. So how do we actually fix that? Well, you know the answer. It's been the answer for the past 24 hours. Merkle trees, yeah. But not only Merkle trees, because Merkle trees have a very tricky limitation. They are great for transparency logs because they're append only. I need to be able to delete stuff. When you start modifying a tree arbitrarily, without rules, that tree becomes skewed. When a tree becomes too skewed, you no longer have log-n access patterns. You have linear access patterns. And that's just why do you have a tree? The classic example of a tree that's actually balanced is the traditional red-black tree. And it's the classic example because it's the tree that's in the Introduction to Algorithms book that everyone here owns at least one copy of. And it's a very simple type of tree with very simple rules governing how to insert, how to delete. And as it turns out, all those rules are based on an operation called rotations. So essentially, rotation works kind of like this. So you want to rotate x once to the right. So x goes up, y goes down. You want to rotate y to the left, y goes up, x goes down. The funny thing about rotation is that here with like the small letters A, B, and C, those are subtrees. We never touch those. If they're Merkle trees before the rotation, they're still Merkle trees after the rotation. And we can kind of combine the Merkle and red-black properties onto a single tree. And what that lets us do is actually, given a partial tree, so given like an inclusion proof on a node of the tree, we can actually start inserting inside that proof. So instead of insert, like I have 3 users I want to add to my set. I have 10,000 users. Instead of having the 10,000 nodes tree, I have the path that my users are going to be inserted in the red-black tree as a proof. I reveal that, which is like 10, 20 users. I insert into that, and the resulting root of the tree is the same as if I had inserted into the full tree. So I have a bunch of examples, but we've decided to turn half of the talk into a conversation session. So I'm going to skip the very nice graphs. But essentially, yeah, we start off with a tree that has a few entries. We add and we add them into the compressed version of the tree, And we see that the root hashes actually match. They're, well, not here, but in that slide they match. Yeah, so what we actually are able to do is essentially we now store all our data as red-black Merkle trees. We have one tree per type of entity, and we are able to both send only the relevant states when we're processing requests, but also when we're processing kind of the meta requests that are affecting state themselves. And that lets us essentially turn an HSM with 2 megabytes RAM, no static storage, into a database, which is very, very nice because we can start enforcing a variety of checks that we would have never been able to enforce before, all essentially right where the keys live, where the keys live. So yeah, it's essentially the best trade-off we could come up with, and I hope you found it interesting.